My name is Jake Robertson, and today I'm going to be presenting my work, An Evolutionary Approach to Interpretable Learning, co-authored by Assistant Professor Dr. Ting in the Machine Intelligence and Biocomputing Lab at Queen's University in Kingston, Ontario. So what's the background for this work? When you think of machine learning, you typically think of classification and regression problems. But in recent years, scientific researchers in various domains have begun to adopt machine learning not only for prediction, but to guide and support their own scientific research. The problem is, these systems are usually highly specialized, complex, and problem-specific, making it really difficult for data scientists in other domains to apply these approaches to their own problems. The opportunity here is that common machine learning algorithms are also capable of learning scientifically valid information, but their black box nature makes these relationships really difficult to extract and understand. To address the problem of black box machine learning systems, the area of interpretable machine learning has emerged. One really good way of shedding light on these black box systems is to look at the feature or variable set of the prediction problem. These approaches are typically referred to as feature investigation and usually measure things like feature importance and feature interaction. However, in scientific problems accompanied by high dimensionality, or having hundreds or thousands of features and variables, widespread redundancy can occur in feature investigation results. In this study, we present a bio-inspired approach to derive feature synergy or feature interaction less redundancy in high-dimensional prediction problems. We explore the efficacy of this approach in deriving scientific insight in two complex domains. So how does our approach work? We repurpose the multi-objective genetic algorithm for feature selection to search for a population of feature subsets that minimizes 1, feature subset size, and 2, the predictive error of a classifier fitted to those features. Due to their low training complexities, we use k-nearest neighbors and support vector machine, but other algorithms can be used depending on the problem. In this selective environment, redundancy in a feature subset is counterproductive to fitness and will eventually be removed by the evolutionary process. At termination, the resulting population of feature subsets is not only compact and accurate, but highly synergistic. Because the genetic algorithm is an inherently random process, and some runs can perform better than others, we run the above steps 100 times, generating a collection of 20,000 feature subsets, and select those on the Pareto front, shown in Figure 1b, for further investigation. In our analysis, the importance of a feature fi is measured by the number of times it occurs, weighted by the size and error of the feature subsets it occurs in. Similarly, the synergy between a pair of features fi and fj is measured by the number of times they occur together relative to the number of times they occur apart. So what were the results? We explore the efficacy of this approach towards deriving scientific insight in two complex domains, bioinformatics and climate science. In bioinformatics, we use the Newfoundland osteoarthritis study to approach the problem of metabolic marker discovery. In the resulting feature synergy networks, an interaction emerges between metabolites involved in the biosynthesis of arginine. Arginine is an amino acid that inhibits cathepsin, which is directly responsible for the degradation of cartilage. In climate science, we use the Notre Dame Global Adaptation Initiative Index to explore the socio-political indicators of climate change vulnerability. In the resulting feature synergy networks, an interaction emerges between population health, medical infrastructure, and sea level rise related impacts. We conclude that feature synergy and our approach to derive it is not only necessary for feature investigation, but sufficient to reproduce years of existing scientific research, a promising outcome for the application of our approach in under-researched areas. Thanks so much for listening, and please feel free to reach out to myself or Dr. Who if you'd like to learn more.